Okay, now let's go to section 21.5. It's called the Maxwell Boltzmann distribution of energy and speeds. What are the units of this? This one measures, the NV measures particles per volume, unit volume, which is per meter cubed, that have energies between E and E plus delta E. So it's the units of it is joules, particles per meter cubed per joule. So NVE measures number of particles that in a unit volume, with energies between E and E plus delta E, right? Number of particles in the unit volume. So it's particles per unit volume per joule, right? And then that's going to tell you the total particles per unit volume with energy E and E plus delta, between E and E plus delta E, right? So the units of the N0 has to also be the same as the units of the NVE, right? Now this one also measures the same thing, but it's a little bit different. It's the NVV measures plus delta V, right? So instead of E and E plus delta E, it's number of particles in the unit volume that are traveling at a speed V, between the speed V and V plus delta V, right? So what are the units of that? It would be particles per meter cubed per meter per second, right? So you're replacing this particles per meter cubed per joule. Then you're replacing the particles per meter cubed is the same, but instead of joule, it's going to be per meter per second, right? So then what will happen? If I want to calculate the total number of particles, how would I do it? The total number of particles would be what? NVE times DE, right? Times the total volume of the box, whatever the container that you're talking about, or it could be in terms of an atom, right? The total volume of the atom, right? So you could have an atom with, let's say, a bunch of electrons in there. A lot of the electrons will occupy the n equals 1 state. Some of the electrons will occupy the n equals 2 state and n equals 3, right? Then this will tell you how many electrons are occupying the first state versus the second versus the third, right? And then if you integrate along all the energies of all the states, right? And then you go multiply by the volume of the atom, that will tell you the total number of electrons in that atom, right? So we can apply it to a gas, we can apply it to an atom or any other system with certain energies, right? So what would happen here? If I integrate that, you would get N0 e to the minus E over KT, right? From 0 to infinity, right? Between the energy of 0 to infinity, V, E, right? It's going to come out as a reciprocal. Then you're going to have the from 0 to infinity, right, times the volume. That's going to be the total number of particles in that gas or in that system that we're talking about, right? So then you have here N is equal to N0 minus KT. And then you put infinity here, you're going to get e to the negative infinity minus e to the 0, KTV, right? The total number of particles in that gas divided by KTV, and that's going to equal this here, N over KTV. This step that I did is called normalizing. Normalizing the distribution, the exponential function. Normalizing means making sure that when I integrate all of this over the total volume of the gas, then the N0 constant needs to be whatever it needs to be so that the total number of particles in the gas is equal to big N, right? This is called normalizing it, okay? So then what is the graph of this and what is the meaning of this, right? So this is the NVE and then this is E. So what this is saying is that the most likely state for particles to be in is in the lowest energy state, E equals 0, right? Of course, quantum mechanically, there is no such thing as the lowest energy E equals 0 because particles have to at least have some quantum fluctuation, right? proportional to h bar, the Planck's constant, right? But let's just assume classical physics here, that energy was 0. So then that's the lowest possible energy is 0 right here, the most preferred state. So then that's going to equal e to the 0 n over kTV, right? Then as the energy is increasing, there's less and less likelihood for particles to want to be in a higher energy state. So what is this saying? Particles naturally, objects naturally like to be in the lowest possible energy state. They like to occupy the lowest energy. And then if you apply this to electrons, that's also true about electrons. Electrons like to be in the lowest energy, but of course quantum mechanically the Pauli exclusion principle prevents them being in the same state. So then they have to occupy the n equals 1, n equals 2, n equals 3 because of quantum mechanical restrictions to their energy states, right? So then as the energy is increasing, the likelihood of particles occupying those energies are less and less and less. Now, how does the temperature change this? As the temperature of the gas goes up, right, what's going to happen? Let's say the initial temperature is 300 Kelvin. If I increase the temperature of the gas, how is the behavior of this function going to change? So this number is going to go up, right? As this number goes up, you're going to have e to the minus, this number is making this thing smaller, right? So you have e to the minus alpha, let's call 1 over kT alpha, and then e, right? Okay, so let's define something. The constant alpha is going to be 1 over kT. We notice that the 1 over kT appears on the outside too, right? So then we have here NVE is equal to, the n over v is the number of particles per volume, right? N over v. The 1 over kT I'm going to call alpha, then e to the minus, then you're going to have 1 over kT is also alpha e, right? So then when the temperature is getting higher, when I'm increasing the temperature of the gas, what's happening? The alpha is getting smaller and this alpha is getting smaller, right? So when e equals to 0, what's going to happen? Right? When e equals 0, you're going to have e to the 0, which is going to be 1. This number is down, so that the gas is going to start out lower, right? It's going to be like this, then it's going to go like this, like this, like this, like this, like this. But the total area under the graph should be what? The total area under the graph is the total number of particles, right? If I integrate from 0 to infinity, right, the total area should not change. So it starts out lower here, so what should happen? It should go like this, and it should be flatter, so it shouldn't go as steep, right? It should go like this, like this. It should eventually reach 0, right? But the total area should be the same. So what happens? That means even though more particles occupy the lowest energy state, right? But that means more and more particles like to occupy the higher energy states too. So as the gas is getting hotter and hotter, 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 the preference for preferring the lower energy states is less and less, and more particles are preferring the higher energy states, right? So if I increase the temperature even more, triple, quadruple, right? Then it's going to look like this. Then it's going to cross that one. Then eventually goes to 0, right? So this is the second one, right? Like this. Then if I increase the temperature some more, make that a different color, then it's going to cross even the red one. I mean, it shouldn't go up. I'm kind of doing it wrong, but it should always be going down. But the preference for the lower energy states should be less and less and less, right? Now, eventually, as you go to infinity, this is going to be so small, and this is going to be, as the temperature goes to infinity, this is almost going to be 0, and this is almost going to be 0. So it's almost going to be kind of like a straight line, you know, where all energy states are almost as preferred to each other, right? Now, what happens as I decrease the temperature? When I decrease the temperature, right? When I decrease the temperature, I'm making the alpha bigger, right? The alpha is getting larger, larger, right? So when the alpha is getting larger, what's happening? When the alpha is getting larger, when e to the 0, you're going to have a larger number. So then the graph is going to start out higher here, then since the total area shouldn't change, then it's going to come down steeper. You see, you can kind of see what's happening there. As the temperature is getting lower, it's starting up higher, crossing it, and then it's going to go. They're all going to go to zero, but it's how fast they're going to go to zero, right? So then it's going to go like this, steeper, cross it, then steeper like this. So what is happening? As I decrease the temperature of a system, the preference to occupy the lower energy state is more and more, right? So then eventually you can reach, can you ever reach absolute zero? Well, you can't really reach absolute zero because all molecular motion would stop. But if I reach close to absolute zero, then it's going to be steep like this, and all the atoms are occupying the lowest possible energy state, right? So humanly speaking, what this means is if the temperature in the room is really hot, and if the temperature of the atmosphere is really hot, people like to get up and do things. They like to go to the beach. They like to get up and hike and be active, right? So they're occupying all kinds of energy states. Some people are resting in the beach. Some people are resting in their home, but others are running around. They're going to the beach. They're doing activities. So the people are occupying all kinds of different activities, all kinds of energy states when the temperature is hot. When the temperature is cold, very winter day, very cold temperature, then the likelihood of people doing a lot of activities is less. Then people like to come in and rest in their home and just kind of sit down and watch TV. So they're occupying lower energy states, right? They're occupying more of the lower energy. So if you compare that to human activity, it is kind of similar, right? Now, we can also apply the same thing to distribution of speeds, right? So this one has an extra, it also has that kT factor here, right? And then it has an extra v squared, and then it's got the kinetic energy. So now if I integrate this, NVV dV, right, from 0 to infinity, that should give me the total number of particles. Now this equation is already given to you so that it is already normalized, right? So if you integrate, then you multiply this by the volume V, right? If you integrate this, so you should be able to get the total number of particles of the gas in that volume, right? When you integrate it 0 to infinity. So it is already kind of normalized for you. We can also do a unit analysis of this to check what the units of this come out just by doing some unit analysis, right? So let's see here, NVV, you have here N, 4 pi of course doesn't have units, 2 pi doesn't have units. The units of mass is kilogram. The units of kT is what? Well, kT has units of joules, because NV squared also has units of joules, so the joules cancel joules. So this one, there is no units at all, right? So then you have here kilogram, then you have joules to the power 3/2, right? And then this one has units of meter per second, and then that's squared, right? So let's see what the units of this is. NVV, then you have here N, then you have here kilogram. Of course, the units of joules are what? Newton meter to the 3/2, meter squared over second squared. Then we have here N is just the units of this constant, which we want to see what it is, right? N. And then we have here kilogram. Then the Newton is already equal to kilogram meter per second squared, right? Meter per second squared. Then I'll multiply this by a meter, right? Then I'm going to raise it to the power 3/2, meter squared over second squared, right? So then we can simplify that some more. We have here, of course, the 3/2 is going to win, and then you're going to end up with NVV. Then you're going to end up with 1 over meter squared over second squared to the 1/2, right? 3/2 minus 2/2 is 1/2. Then that's going to equal 1 over meter per second, right? Which is going to be in seconds per meter, right? So then you can kind of see what's happening here. If I do NV dV, what are you going to get? then you integrate this from 0 to infinity, right? When you do NV dV, you're multiplying this by meter per second. So then when you multiply this, the N by second meter, when you multiply it by meter per second, the meter is going to cancel, second is going to cancel, and then the units of the NV, are the same as the units of the N, right? They're already the same units. So the units of the N are particles per volume. Okay? This one we had N over KTV, e to the minus E over KT. If we want to define this the same way as the N in this equation, we can say the N, let N equal N over V. The previous way I defined the N was that the N was the total number of particles, but I could also define the N as particles per volume. Then I can just rewrite this as N, right? And then make it the same meaning as this N. So this N is already the particles per volume occupying in that gas, right? And then this one is going to be the same, particles per volume, and then you're going to have here KT, okay? So then the units of the NV is also going to be particles per volume occupying energies E, between E and E plus delta E, and this is going to be between V and V plus delta V. Okay, what's the shape of this function going to be? Okay, so since it has this extra V squared down here, when V is 0, it starts out as 0. Okay? So that means if you have a certain temperature in the room, that the gases, which gas particles are moving at the velocity of 0? None. Okay? And then no matter how hot the room is or how cold the room is, there's always going to be some molecules that are moving at a certain speed, right? So the likelihood of a particle going at just stopping is 0, basically. So then as the velocity gets bigger and bigger, the number of particles moving at that speed gets more and more and more. So this increases, right? But then this one likes lower velocities. You have, when the V is 0, e to the 0 is a maximum, right? So you have the product of two functions. This function gets larger and larger as the V gets bigger, right? You have the function y equals V squared, basically. It likes higher velocities. This function likes lower velocities. So if I graph just this function, when the V is 0, the exponential function is 1, right? E to the 0 is 1. Then when the V gets bigger, it likes lower, it gets lower. That means it likes lower velocities. It's saying that the particles have a more likelihood of occupying lower velocities. Well, this one is saying, no. Particles have a more likely probability of occupying higher velocities. Well, if we multiply these two, we get a Gaussian curve, right? It goes like this and like this. So when this is 0, you multiply 0 by 1, right? The 0 trumps the 1, and then the answer is 0, right? As this gets bigger, this one's getting smaller. You're going to get like this, then it's going to reach a maximum, then it's going to get less and less. Why? When this goes to infinity, you have e to the minus infinity, and then this also gets infinity, y equals infinity squared. Which one trumps that one when we multiply them? Which one is bigger? Infinity squared, is that a bigger number versus infinity, e to the minus infinity? It ends up that the limit of this function is 0, right? You can do L'Hopital's rule on this, right? And you can say which one is bigger number, v squared or e to the v squared, right? Take the limit of that function. So as v goes to infinity, right? So infinity squared versus e to the infinity squared. Well, e to the infinity squared is going to trump the v squared by a lot. So if you put infinity here first, you're going to get infinity over infinity, so it's undetermined. But L'Hopital's rule says I can take the derivative of the top, take the derivative of the bottom, you're going to get e to the v squared times 2v. So they're both infinity still, right? So now if I put infinity, you're going to get 1 over infinity, which is 0. So that means the e to the v squared is killing the v squared. It's much, much bigger number. Well, the same thing holds true with e to the minus v squared. If I put infinity here, it's much, much smaller number than this big number, right? So that means as the velocity is getting larger and larger and larger and larger, right, the likelihood of particles going that fast is very small. So that there is a certain peak. This one we call V most probable. VP, you can sometimes they write it MP most probable or VP. That means at that velocity, there are the most number of particles, the most likelihood of traveling at that velocity, right? Now what's going to happen to the shape of this function as I change the temperature, right? So you could make the same kind of argument that we made with energies. I have y is equal to alpha v squared. So this function, since alpha is getting less and less, this function is getting flatter, 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 right? Like that. And then this function is also getting flatter. Right? So then it's looking more like this. Like this. So that means since they're getting flatter, they're not peaking very quickly. That means the higher velocities are more preferred now. So the behavior, the shape of the function doesn't change, but then the behavior changes in that it spreads out like this. It spreads out. Let's do it with a different color. Like this, like this, like this. Like this. You see? So that means one of the things that happens is the most probable velocity gets higher. That means the molecules are going to be on the general traveling faster, right? The spread of the velocities is also going to get wider. That means there's still going to be some particles that might be traveling near zero or very slow speeds. And there's going to be some particles that travel very, very fast, but it's still going to have to die down to infinity. And since the spread is getting wider, the total surface area shouldn't change, the total area of the graph. That means this peak gets less, less like this, right? And that means there aren't as many particles traveling at the most probable velocity, right? Because the spread is more. So if I make it hotter, hotter, that's exactly what happens, the tendency. It goes like this, it spreads out more, then it goes like this, like that. Almost like a black body radiation thing, right? The curve that we study for black body radiation. So it goes wider like this. There are less number of particles traveling at the most probable speed. The data gets wider, right? Well, what happens when the opposite, when I decrease the temperature of the gas, right? When I decrease the temperature of the gas, the alpha goes bigger, right? And then this alpha gets bigger, right? Because alpha is 1 over kT. Now I am decreasing the temperature of the gas. The alpha is getting bigger, right? So then you have the equation y equals alpha to the 3/2 to the v squared power. So if alpha gets bigger, it's going to look steeper, right? And then the e to the minus alpha, right, is going to be also steeper, like this. So that means more of the data is on the lower side, right? The exponential function is going down steeper and steeper, right? Like this. So the lower, this is the velocity, the lower velocities are a lot more preferred. This one says the higher velocities are still preferred, but since it's peaking very fast, right? That means the dominance of the velocities are more to the left. So now if I take the product of these two, you're going to end up getting like this. A curve that looks like this. The most probable speed goes less. There are more particles traveling at the most probable speed, and the distribution of speeds is less too. So it starts peaking, right? Then it goes like this, right? And then if I decrease the temperature more, like this, the total area shouldn't change. The total area here, 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 all of them should still be the same. So there are just more particles traveling at the most probable speed, and the distribution of the speeds is less, and there are less particles traveling at higher speeds, right? So we can kind of see the meaning of the graph of this function and the previous, the Maxwell energy distribution function, right? Then we can now calculate what Vp is. There are three speeds that are very important, but the most important is called the root mean square velocity, right? That one, since it's the one that maximizes the NV, all you do is you take the derivative of this, set it equal to 0, right? So then you're just going to say n dn dv. These constants aren't going to matter. You're just going to take the derivative of this guy. So you're just going to get 2v e to the minus mv squared over 2kt plus then v squared, and then take the derivative of this guy. All right. Then you're going to set this equal to 0. Then you have to take the derivative of the inside, which is minus 2mv over 2kt. Then you're going to set this equal to 0. You can factor out the v and e to the minus mv squared over 2kt. Okay, then you're going to have 2 plus, then you're going to have here v, then you're going to have the 2 and the 2 cancels, negative mv over kt, set it equal to 0. So of course, this one we don't worry about, make sure that this is 0, right? So then you have here 2 minus mv squared over kt is equal to 0. V is equal to square root of 2 kt over m. This is the value of the most probable speed. In other words, most number of particles are traveling at this speed. This is Vp. We could also write it as 2 k over m is the gas constant over the molar mass. This is more preferable because a lot of times we don't know the mass of each particle, but we know the molar mass of the gas. And then instead of the Boltzmann's constant, we know the gas constant. So this is 2RT over M, and then we can write it that way. A lot of times what they also do is they rewrite this so that it's in terms of the Vp, right? So you can kind of rewrite it this way. Then you have here NVV. Then you can say, okay, 4 pi n. You have here m over 2kt, m over 2kt. You see? M over 2kt. That's going to be what? Is equal to 2kt over m. Right? So then when you see here m over 2kt, m over 2kt, that's going to be 1 over Vp squared, right? So then we can say here m over 2kt, that's going to be 1 over pi Vp squared to the 3/2 power, right? And then we're going to say v squared e to the minus, and then m over 2kt is going to be 1 over Vp squared, so it's going to be v squared over Vp squared. So it's kind of an easier way to write it. And then we can kind of clean this up a little bit more. You can say 4 pi n, and then you're going to have, you can factor out the pi to the 3/2, pi to the 3/2, put it on the outside, and then you're going to have v squared, Vp squared to the 3/2 is going to be what? Vp cubed over Vp squared. So you can see v squared over Vp squared, v squared Vp squared is the ratio of the velocity of any gas molecule to the most probable velocity. Then you're squaring that, and you're saying e to the minus that power, and then the same quantity is appearing here squared. Then you have an extra Vp here, then you have pi to the half. So you can kind of tell what the units of this are going to be, right? Particles per unit volume divided by the unit of this, which is going to be meter per second. This one doesn't have units, and that one doesn't have units, because the units of this cancel the units of this. So you have 1 over meter per second. So you can see, if I multiply this by dv, which is the change in velocity, then I can say this one measures how many particles are moving with a velocity v and v plus delta v, right? So if you multiply it by dv, the meter per second will cancel, and you'll get particles per volume. Okay. Now we can talk about what the other possible velocities are. The other possible velocity is called the average velocity. Okay. The average velocity. The average velocity will be overall, what is the average speed of the particles in that gas? So how do you find average velocity? You do nv dv. Basically, it's however you find the average velocity, right? The average of any function. To find the average of any function, you do x over v minus a, right? You integrate that function, from any point A to B, right? And then you divide it by the interval. So you say here V and V dV. This is measuring how many particles are moving with a speed V and V plus delta V. Then you multiply it by dV, right? Which is this velocity. Then you integrate this here, 0 to infinity. And then you divide it by the number of particles per unit volume of that box, right? So this is the number of particles divided by volume, divided by meter per second. Multiply it by meter per second, which is the dV, and then that will cancel. Then you multiply it by a V, which will bring the meter per second back. Then you divide that by the total number of particles, which is going to be particles, and then this is particles per unit volume. Then this one cancel, and then the units will match, right? Of course, this end and this end will cancel, right? And then we're going to say V average is going to equal 4 over pi to the half Vp, right? And then you're going to have, well, this Vp squared we can factor it out of the integral, make this Vp cubed, right? Then you're going to have here integral 0 to infinity. Okay, you could do U substitution. You can say let U equal V squared over Vp squared du is equal to 2V over Vp squared dV, right? So then you can say here, so V average is going to equal 4 over pi to the half Vp cubed, right? So then you have here Vp squared comes out, and the 2 comes out. So then you have 0 to infinity V squared e to the minus u du, right? And then V squared is going to equal, P squared is going to come out. Let's see what happens here. So this 2 cancels, this one becomes 2 over pi to the half. Then Vp squared cancels the one of this, so you have Vp, right? But then another Vp squared comes out. So then you have here integral 0 to infinity u e to the minus u du. And then the Vp cancels this Vp, and then you basically get that, right? So this is V average. Then you're going to integrate that. What is the integral of that? This is a pretty well-known integral in calculus, and when we perform this, we just basically get 1. So the V average comes out to be equal to 2Vp over pi to the half. So we're going to multiply this by 2, right? 2 over pi to the half, square root of 2RT over m. One of the things we see is that V average is a higher number than Vp, right? What is 2 over pi to the half? Let's calculate what that is. 2 divided by pi to the power 0.5, 1.128. 1.128. So we can say the Vp divide we can say the V average divided by Vp is 1.128. So the average speed of molecules in the gas is going to be 12% or 13% higher than the most probable speeds, right? On the distribution of gas graph, right, which looks like this. So this is Vp, right, which equals to square root of 2RT over m. The V average is going to be a value 1.128 higher than that. So 12.8% larger, right? And that's going to be equal to square root of 8RT over pi. The pi to the half should disappear, right? It should just be pi, because when I bring pi to the half into the radical, it should just remain as pi. So then it should be pi m. So what is happening here? That means even though there are the most number of particles moving at the most probable speed, on the average, particles are moving faster because a lot of them are moving faster than the most probable speed, right? There are the most number of particles moving at Vp, but if you take the average speed of all the molecules, there are a lot of particles moving faster than that, and so that pushes the average speed faster than Vp, right? So this one is going to be V average greater than Vp. But even the V average doesn't have all that meaning. There's another speed called V root mean square, right? And that's equal to the square root of the average of the squares of the speeds, right? So then to find the V root mean square, you're going to do the square root of the average of the squares of the speeds. Okay? So first you're going to find the average of all the speed squares, then you're going to take the square root of that. So then how do you do that? V squared average is going to be, so then you're going to do here V squared NV V dV, right? 0 to infinity, divide by N. Right? This is the average of all the speed squares. So you're taking the speed of every molecule, you're squaring it, right? Then you're adding up, you're multiplying it by how many particles are moving at that speed, right? You're squaring the speed, you're multiplying by how many particles are moving at that speed, then you're integrating that from 0 to infinity, dividing by the number of particles, right? But this one is going to give you units of what? This is going to give you units of meter per second squared. The n and this n will take care of themselves so that the particles per unit volume will cancel, but it'll be meter per second squared. Then I'm going to take the square root of that, and then it'll give me meter per second, right? So in order to do that integral, you're going to go through some of the similar steps that we did, n, v, v, then you're going to have here, okay? Now, in order to integrate this, we actually have to use a technique. You have to do it in polar coordinates and use the results that you get, 0 to infinity to the power of 4th e to the minus alpha x squared dx, right? So we have to be able to integrate something like that, and you learn the techniques of integration for that in calculus 2, and we use polar coordinates to integrate that, and we get the result. So then when you integrate that 0 to infinity, and then we solve for this is the V root mean square. So then we take the square root of that. The final result comes out. The final result comes out to be square root of 3kt over little m, or square root of 3RT over m. This is the same as the root mean square speed that I talked about earlier on in this chapter, when I talked about the kinetic energy of particles. Half mv squared is 3/2 kt, and then remember I said each degree of freedom of the gas contributes a half kt, right? So then you have here the 2 and the 2 cancel. V squared is equal to 3kt over m, and then v is equal to square root of 3kt over m, right? So this is the same result that I talked about here. So the root mean square speed is the most significant speed because it's connected to the kinetic energy of particles, right? The kinetic energy of particles depends on the speed squared. So what is most important? The average of the squares of the speeds of the particles, right? The average of the velocity squared of all the particles in that gas, right? So then, what would that equal? So then it ends up being V root mean square is equal to square root of 3RT over m. Now, would that be greater than the average velocity? Would it be smaller? Where would that fall? So let's compare all three of them. V root mean square, the average was square root of 8RT over pi m. This is the molar mass. And then the V probable is square root of 2RT over m. So this one is 2, right? This one is 8 over pi. And we saw 8 over pi is larger than 2, right? And then this one is 3. So if I compare V root mean square divided by V most probable, what do I get? So that's going to be square root of 3 divided by square root of 2. which is going to be square root of 1.5, 0.2247. Okay, so the root mean square speed is 22% larger than the most probable speed. The other one was 12% larger, right? So the v root mean square is here. V root mean square is even larger than the most average velocity, right? So larger than v average. I can also take the ratio of v root mean square over v average. Square root of 3 over square root of 8 over pi. Right? So then you can say here square root of 3 pi over 8. So 0.85. So you can say the root mean square speed is 8.5% larger than the average speed. You see? So this is larger than the average speed, which is also larger than the most probable speed. Right? So that is the speed that has the most meaning. A lot of times they will also rewrite this way. They will express this as a constant c is equal to square root of RT over n, some constant c, and then this has units of meter per second. So then they're going to say V probable is equal to square root of 2c. V average is going to be square root of 8 over pi c, which is going to be larger than V probable. And then V root mean square is going to be square root of 3 c, right? So the c already has the radical, so you don't need another radical here, right? So then you just have a number. So square root of 8 over pi is larger than square root of 2. Square root of 3 is larger than square root of 8 over pi, so then this is going to be larger than Vp. Okay, next I'm going to do a simple example illustrating the differences between these speeds and how to find them. And then after that we'll do several other examples, okay? Thank you very much.